This presentation is on the stage 2 topic of electric fields. So let's start with an introduction. So back in the 6th century BC, so quite a while ago, 2600 years, the Greek philosopher Thales found that when he rubbed amber with a cloth, and then he put the amber near some particles, the particles were attracted to the amber, so such as dust and grass. The unknown force that caused this attraction is called the electric force, and this is after the Greek word for amber. Alright, so sometime later, 17th century AD now, so only very recently in the scheme of things, Otto von Guericke, he observed attraction and repulsion of charges. Say for amber, the particles were attracted to the amber. When you have two pieces of amber that are charged, they actually repel from each other. So there was two opposite forces acting in that situation. Later on, Benjamin Franklin introduced the terms positive and negative to describe the nature of these charges. Now, on a smaller scale, the positive charge is actually produced when you have an absence of electrons or less electrons than there should be. And a negative charge is when you have an excess of electrons, with electrons being a negative charge. So introducing Coulomb's law, any two stationary charges experience mutual force along the line joining the charges. So this is very similar to the force of gravity between two objects. So you can see in this bottom diagram, we've got a positive and a negative force. Now we know that there's an attraction between the two because they're opposites. This attraction, this force, acts on a line between the two particles. Where we have two particles that are of the same type, both positive in this case, they're going to repel each other, and they're going to repel each other in the opposite direction. So if we move these vectors, instead of, say, a pull type action, we've got a push type action on this particle. We also see that the force acts along the line joining the two centers. Now these particles, even though they're drawn as circles, they're actually infinitesimally small. Okay, so Coulomb's law states that the magnitude of electrostatic force between two charges is directly proportional to the magnitude of the charges and inversely proportional to the square of the distance between them. And you can see this is demonstrated with this equation. And you can also see that this is very similar to the equation of gravity, where we've got G in our equation of gravity. Here our constant is a different value when we're talking about charges. So the charge of a particle is represented by Q, and when we've got two particles, we've got Q1 and Q2. In the International System of Units, the unit of a charge is a coulomb, denoted by the letter C. R in this formula represents the distance between particles, and epsilon, this E, is the permittivity of the medium. Now in physics at year 12 we talk about particles in a vacuum, so we'll use a value of 9 times 10 to the 9 Newton meter squared per coulomb squared when we're talking about this, and that this value here represents this whole constant at the front, and you can see that clearly on your formula sheet. So when we've got two particles, the force on each particle is equal but opposite. So this is a direct application of Newton's third law. So we can see in this example, if we have sphere A and sphere B with a charge on each sphere, separated by a certain distance of r, we can find the force using this formula. Now the force is the same for both, however in opposite directions. Even if the values for this sphere and this sphere were different, the force will still be the same, however in opposite directions. One thing you can look at in your intended student learning outcomes is the requirement to demonstrate your understanding of proportionality. So when we've got this equation here, the force is proportional to the charge of the masses. So say if we double Q1, then the force is also doubled. Now you can also see that the force is inversely proportional to the distance squared. Well, if we double the distance, that means this term is 4 times larger, meaning the force is a quarter of the original size by doubling the distance. Alright, so Coulomb's law allows us to find the force between two charges only. If a third one is introduced to the system, we'll have to calculate the force on that particle due to the other two particles and add them using vectors. So this is what we call the principle of superposition. So this is just saying that a force at a point is actually the result of a number of forces due to the other individual charges, and then the total force is found vectorially. Alright, so talking about electric fields in general, well, we have forces that are contact forces, where the two particles or bodies are in contact and a force exists between them. So this could be like friction or something like that. Non-contact forces is where there's a separation between the bodies, yet a force still exists between the two bodies. This is an example of action at a distance. Back in the day before the 19th century, these forces were considered to be direct and instantaneous between the two bodies. However, this has been further developed. So if we think of an example where we've got two charged particles, they're not in contact. How does one know about the presence of the other in order to exert a force on it when they're not touching? Or when there's a distance separating them, say if that distance is increased, how does each particle know to exert less force on the other particle? Like if they've got no contact. So they must communicate somehow. So in the 19th century, Faraday developed the concept of the electric field to explain this interaction. Right, so if we think about our charges, each charge somehow modifies the properties of the space around itself, creating an electric field in that space. So if we don't worry about the particles themselves, think about the electric fields interacting with each other. So the information between the distance of the particles themselves is transmitted from one another via the electric fields. Right, so when we think about action at a distance, we're talking about interaction between two particles, but in the case of electric fields, we're talking about the fields themselves interacting rather than the particles. So now I'd like to cover how to draw electric fields. Right, so in all fields, the lines of force are drawn so that the number of lines in a certain area is directly proportional to the strength of the field. So if we look at this one on the left, for example, that around the particle itself, the lines are very close together. So this suggests that the field around the lines is strong. Now if we go further out, away from the center of the particle, the lines are further apart, suggesting that the field is weaker than it is in the middle. Okay, the direction of the lines is also important. The direction of the lines indicates the direction of the force that would be experienced by a test particle. When we talk about electric fields, the test particle would be a small positive charge. So if it was released at any location within the fields, the lines would indicate the direction it would go. So if we look at this example on the left, if we release a positive test charge in this location, it will be repelled by this charge in the direction of the arrows. And you can see as it moves, it will move around in this direction, suggesting it is attracted to this charge. So as a positive test charge is an opposite sign to the negative, it will be attracted to this charge. Now, the lines of force always arrive and leave a surface at right angles. And the lines of force never cross each other, otherwise you'd have multiple forces acting on one particle. In this example here I've got infinitely long plates that are charged, and you can see the electric field that is present between the plates. You can see the lines are uniformly spaced and the field strength is constant. Okay, when we've got spheres, the only place the charge can go in a sphere is on the surface, as it is hollow. So that's where the charges are. And the electric field propagates from the sphere. Now, inside the sphere, there is no electric field, as the electric fields from opposite sides cancel, as well as there being no charges in the middle of the sphere. Now the strength of an electric field is defined as the force per unit test charge placed at that point in the field. Alright, so let's look at a derivation. So if we wanted to find the electric field strength at point A due to a particle Q that's charged at a distance r from that particle, we can put a small test charge at point A. Alright, so Coulomb's law will give us the force on that charge. Alright, so we've got our force equation here that we've seen before. Combining this with our equation for the electric field strength, we can take this force, substitute it here, and what we're left with is this equation for electric field strength. Now we can see from this equation that the strength of the field is directly proportional to the magnitude of the charge and inversely proportional to the distance away from the particle. So we can see the magnitude of the electric field is the same for all points that are the same distance from the charge.